All right, so this is looking out 100 megaparsecs. You can see our local group, which is actually part of when you get clusters of clusters, they're called, as it says right here, superclusters. And so we're actually part of what's called the Virgo supercluster, which of course includes Virgo and some other clusters of galaxies. But here there are some more. When you look out, we're trying. So the idea here is to look at the universe, and the universe of galaxies, of course, which are collections of stars. Remember, ultimately it has to do with stars as well. And the stars are gravitationally linked. The clusters are gravitationally linked to each other, and the superclusters are gravitationally linked to each other. But there are these spaces in between, and we'll look at that in a little bit more detail. So this is a giant survey that has taken place in I think it was Harvard that did this most recent survey. Anyhow, it doesn't matter. One of the things that we find, this is just looking out into the universe, I should say, and we find regions where there are large numbers of not large numbers. These are all galaxies. Every one of these dots is a galaxy. And notice we find regions where there are no galaxies, just like this picture right here shows. There are these regions that don't have, and they're giant like bubbles, if you will, where there's almost nothing at all, and they're called voids. And when we get to cosmology, which is the next chapter, we have to be able to explain why it is there's some regions of the universe where there's absolutely no galaxies, and there are some regions of the universe where there are these giant strings of galaxies or filaments of galaxies. This one right here is sometimes called the Great Wall of Galaxies. It has a little nickname, as a lot of things in astronomy have nicknames. This one's been known for a while now. When did we first? I don't know how long. Anyhow, notice you get the same kind of thing with in the southern hemisphere as you do in the northern hemisphere. We're just looking out into the universe. This is showing us the distances in megaparsecs, right? So, these are things going out all the way to about 750 megaparsecs, so 750 million parsecs. So we're seeing voids, we're seeing filaments. These are, or some people like to call them strings of galaxies. There's of course a wall as well, and the walls are just they're just more a collection of more galaxies, or more, I should say, more superclusters. So it's kind of like where the superclusters like if you think of the bubbles, right? The bubbles are where the voids are, and then where the edges of the bubbles are where these filaments and sometimes if there are enough of them in a particular direction, that's called a wall. And the wall and a filament are basically the same thing. It's just there's for something to be a wall, it just has more galaxies. All right. It's kind of it's not. It's semi-technical. It's not really. It's just we're looking at structure, right? Overall, huge volumes of space. What does the structure of space look like on a large scale? So that's what they're talking about. All right, and in fact, that this when we go out into the universe, it turns out that this is what we see. So even when we go even further than this, further than 700, so we go billions of light years out, we still see this same kind of thing: superclusters, we get voids and filaments. All right. So quasars, we know that quasars are extremely distant. We think that they are a stage in galactic evolution where, the galaxies have just merged. Remember, you got to keep in mind, even though this is the next chapter, more material about the next chapter, the universe was a lot smaller in the distant past. You go back 10 billion years, it was a much smaller volume. So collisions between galaxies was much more frequent, and during those times when there were these galactic mergers, that's when you have the age of quasars, right? Let's see. So this is something else this is something that is quite interesting when we look at there's a one particular transition between the electron in a hydrogen atom. Of course, you're talking about the majority of the universe made up of hydrogen, or at least the majority of the visible universe made up of hydrogen. So when an electron jumps from the ground state to the first excited state, that's called the Lyman. The Lyman transition. It was just a guy that named that particular transition. It's a well-known transition of in a hydrogen atom, in a neutral hydrogen atom, and it's at the wavelength is 122 nanometers. All right, because we know that wavelength, that's a very well-known transition, and so when we look at the quasars, you have to understand the light from a quasar has passed through many different gas regions, stellar regions, past galactic clusters, past lots of dark matter out there, and so each time that the light, let's say light from some distant quasar more than 10 billion light years away, as that light was passing through the photons were heading in our direction, there was absorption in this Lyman. This particular Lyman transition, which again is in the infrared. Is in the ultraviolet, but because of the redshift, the stretching of the expansion of space itself, these Lyman transitions get stretched out. And so this is sometimes called the Lyman forest, right? That's the Lyman alpha forest. The alpha is the transition between the ground state of a hydrogen atom and the first excited state. It's just, it's a well-known wavelength that people can remember, the wavelength of 122 nanometers. But what happens is, of course, as the universe has been stretched out, as the light has traveled from some distant quasar to our telescopes, it's encountered lots and lots of things, and so each time there's some absorption that takes place, and it's a little bit of a record of the journey that these photons have taken, and so we're just now able to basically tease out some of the information from this so-called Lyman alpha forest. All right, so that's just. Let's see. The universe at large scales. This appears at first to be. So this is the situation that happens with quasars. With some quasars, that they are oriented in such a way. This was one of the first ones that was discovered this way. Is they looked like there were two quasars that were basically identical. They had the exact same absorption lines, and they had the exact same redshift. And people were like, what's going on? And so very soon people realized, hey, wait a second. This double image is actually just one quasar that as the light passes near some really massive object, including the dark matter around that particular massive object, I'm talking about a galaxy, of course. What happens is, according to Einstein's theory of general relativity, the light gets bent, and so you can have the light bending, and this the light can come from two different places when it gets to, or appear to be coming from two different places, image A and image B, but really it's the same object. It's just that as the light was traveling from this distant quasar billions of light, at least 10 billion light years away, it encounters this, and so that light gets bent. And that's actually, it can happen more, that you can get more than just two. Let's see if they show us a picture. So yeah, this is one. Sometimes this is called an Einstein cross, because Einstein actually predicted this, where you'll actually get 4 images of the same quasar. Because of course, this is happening in 3 dimensions. So, oops, didn't need to go back that far. So that's sometimes called an Einstein cross. You're seeing that here in these 2 images. And then, of course, we're seeing lots of this gravitational lensing. So, of course, that's called gravitational lensing. Now, things have to line up exactly right for this to take place. That doesn't automatically take place. But, of course, when something's 10 billion light years away, when the light traverse that distance, there's bound to be something in the middle, something in between where, and in fact, sometimes multiple times you get these gravitational lenses that take place. And in fact, well, one of the things that can happen actually is there can even be a delay where you'll get the image from one side, and then over just sometimes it's a matter of minutes, sometimes even a little bit longer. You'll get the exact same image in a different portion of the sky, and that has to do with these multiple gravitational lensing that takes place. All right, so this is actually a really wonderful image that shows all of this gravitational lensing that's going on. So you have this really massive. I would probably say that that's an elliptical galaxy with a super giant elliptical, and so you're getting all of this gravitational lensing that takes place, and you see it over here in this other picture. And let's see. And the other thing that we can do with this, when we get gravitational lensing, is we can map. And I mentioned this before. We can literally map the dark matter. Again, we can't see it, but when the light is coming from behind the dark matter, the dark matter, of course, acts gravitationally. That's the one thing we know that it does, and it'll bend the light. And so we, using supercomputers, we can basically map where the dark matter is. Let's see. This composite image shows 2 clusters colliding. And so they're just showing that when these clusters collide, it leaves there's still a whole bunch of matter in between that heats up, and that matter, of course, was already there. That's a matter that was from mostly hydrogen and helium from the Big Bang itself, and so that's this intra cluster gas. All right, and that's I think that's about it. Let me go over, make sure I've covered everything. Galaxies' masses can be determined by the rotation curves, and of course the motion of the clusters can also determine the overall mass of the clusters. Let's see, measuring large amounts of dark matter. When we measure, of course, when we measure the rotation curves of individual galaxies, we know that there's got to be dark matter, not just dark matter around our galaxy, other galaxies too. And then, of course, clusters, right? The clusters need a whole bunch of dark matter to keep them together. So there's a whole. It turns out there's more matter. We don't know what it is actually. There's more dark matter than there is luminous matter, the stuff that interacts with light. We're not exactly sure why. That's a big mystery of 21st century astrophysics. We're trying to figure that stuff out. All right, remember, collisions, mergers are very, very important for galactic evolution.